today we sort of move on to a new topic, monads. But before we get there, I just want to sort of recap and just remember where we are in this story, right? So part one is just going to be a recap, and in some sense, some motivation for where we're going next. So far, we've been talking about categories and we're talking about programming, and in particular, the constructions that are sort of most relevant at the intersection are these notions of types and functions. And so in our analogy, the types form the objects of the category and the functions form the morphisms. And from a programming perspective, we're interested in ways of constructing types to sort of structure our computation, and then ways of constructing functions to do the computation, right? So last week we talked about universal constructions, like products, coproducts, function types, and so on. And the basic idea here was, given some objects in a category, or in particular given some types, we sort of get a new type, a new object, right? So for example, there was this notion of a product type. We sort of take two types, A and B, and they come along, and then they turn into, the built-in syntax is just the pair type, but we also wrote sort of explicitly this sort of pair type, pair AB, right? So given objects, we get a new object. And not only from that, with this notion of universal constructions have universal properties. And this gave us a way of taking some functions and getting a new function, right? So with this product type, we had this idea of tupling, which is sort of expressed through this function of type sort of tuple, well, called tuple, and it says if we want to construct an arrow to, if we want to construct a function into a pair, then I can take a pair of functions, C to A and C to B, and I get a function from C to the pair AB, right? So this is ostensibly a harder problem, but it can be solved by solving these sort of two easier problems of constructing functions into the factors. OK. Then after universal constructions, we talked about sort of coalgebras for a functor, or algebras and coalgebras for a functor. We talked more about algebras, but we sort of made this observation, in particular David on Wednesday made the observation that you can sort of dualize this, and it has a more infinitary nature. But here we talked about the process was given a functor, so we can construct a functor, an endofunctor in our category, or a functor, an instance of the type class functor in Haskell, and we get a new type, an object. And so this, well, this was sort of a way of constructing what are called algebraic types, or algebraic data types. This was a way of dealing with recursion. So given a functor, say one functor we defined on objects, took an object x and mapped it to 1 plus, say, int times x, right? So we can take this functor, and we get this recursive data type called lists of integers. And so we have this way of constructing types. And again, these are specified by some universal property. And this universal property, this sort of for every blah, there exists a unique blah, or exists a unique map. It gives us also a way of constructing functions. And this time, they're recursive functions. So for example, so in particular, we had this idea of a catamorphism for these initial algebras. And so in this case, what it would do is it would take an algebra for this functor, so a map from FA to A, and it returns this catamorphism, which in this case is this map from list int to A. So we think of this as, and I can put these parentheses just to help readability, although of course Haskell automatically puts them in. But what's going on here is that F is sort of expressing, an algebra is expressing some sort of one-step computation or evaluation for this recursive type. And this notion of catamorphism lifts it to a recursive function over this entire list thing. OK, so that's so far. We've talked about how to construct types and how to construct functions. And in fact, this sort of language of algebraic types and algebraic functions and recursive types is really as powerful as you need to sort of write basically whatever function you like. I'll just end the statement there. But so this is a really nice framework, for talking about functional programming, constructing functions. And it gives good ways to reason about them. But as you write programs in some practical sense, it's a bit too limited if everything's purely functional, right? You want to be able to interact with your program. You want it to be able to handle data, so you want sort of input and output. You want to be able to read in values. You want to be able to write out values or write a log or something like that. And so we need some tools to sort of, we have a nice way of talking about functions, as we have a very solid theory for thinking about programming, but we want to make it a bit more practical. We want to sort of be able to escape from this rigid world, which is really nice for reasoning and constructing, and perform some more practical tasks. So here we want to talk about something like a side effect. But what about side effects? And really, I really want to speak a bit more general than just about this notion of side effect. This is an informal term, but it's not a bad way, not a bad step into the sort of thinking we're trying to talk about. And so the basic idea here is, so example is something like logging, right? Writing a log of what's happening. So I have a function like int to int, and that's all very well. I defined it nicely using the structures that we've already talked about. But it might be the case that I want to sort of just keep track of what's going on in the computation. So I really don't want just an integer to come out of this computation. I want some message, some string that describes what happened, that will alert me to errors, that will just help me understand what's going on in the machine. So that's all very well. I've got a type int times string that can describe what that function is. But say I want to do this for all parts of my computation. And my computation I'm just thinking about as sort of composing these functions. So I have a function from int to int. I want to compose that with a function from int to bool, right? That's what I want to do next with this integer that's the output of this combination. And I also say I want to write keep some log of this computation. So that's really the sort of two functions that I want to execute. But the structure here is now a bit off, right? I can no longer compose these because my compiler is keeping track of the types of these functions, and these types don't match, right? So how do I sort of think in terms of constructing? I'm trying to think in terms of the first computation takes an integer, returns an integer. The next one takes an integer, returns a Boolean. But it's sort of producing all this stuff we need to keep track of on the side. And I want to organize that in some way. So one way to think about what's going on is that this sort of time string thing, it's a really nicely structured thing. David introduced it sort of last week as a functor, right? So maybe I'll just call this we'll call the functor s for time string. And this type is sint, right? And so now I have a map from int to sint and a map from int to sbool. So one way, if given this sort of functorial construction, I can think about composing these now is applying fmap, applying the action of the functor to this morphism. And now, given a map from int to sbool, I get a map from sint to s of sbool, right? And so this at least helps me compose things a bit, because now these types match up. But when I compose them, now I get a map from int to sbool. And so I'm sort of producing these strings, but I sort of have lots of copies of this factor string lying around. And so what I want is some sort of framework where I can sort of take this sort of collection of strings that I'm producing and just reduce them down to a single string, which is the log. So I want some way of relating sbool with sbool. And I want that, in fact, for any type bool that I can put in. right? So what's important to notice here is sort of this notion of taking two things of something and returning one thing. And so we can return sort of out of our basic ideas of composition to try and construct a framework for thinking about this. Right? So we've been talking a lot about categories, but really the sort of basic structure that I want to remind you of that is the starting place for thinking about composition, I claim is really just a monoid. So recall what a monoid is. So what is a monoid? A monoid has sort of three constituents. We have a set, and what we want to do is we want to talk about composing elements of that set, right? So given one way to do that is given two elements of the set, we return an element of that. So a monoid, let me sort of figure out some notation. That's how a monoid is a set M of things that we're going to compose. And then the way I'm going to talk about this composition is sort of, I'm going to call it a binary operation, but really that's sort of jargon getting thrown in. All you need to pay attention is just to a function that takes two arguments and returns a single one, right? Takes two m's, returns an m. And then we also have this thing called an identity, which is sort of like the do-nothing aspect of the composition, the zero. So I'm going to call that a nullary operation. And this is just an element of m. So, I mean, example you might have in your head is the natural numbers under addition. And so we have the natural numbers, we have plus, and we have 0. But instead of thinking of this as an element of m, we're seeing we can equivalently just think of it as a function from 1 to m. And this is a sort of more point-free perspective on what's happening. So this is the data of a monoid. It's a framework for thinking about composition. And we want it to be sort of well-behaved. So it obeys some laws. So the first are the two unit laws. And what these say, again, I'm just practicing writing things in a more point-free style, so they might look a little unfamiliar. But the idea is if we start with an element, let's call it x of m, what we can do is we can produce this pair x, right, from using the fact that we just have this element of e of m lying around. And now we can apply our multiplication, and we get back to m, and this should be the identity. So what's this saying? It's saying if we do this, it's e times m, but if we go around this way, x mapped through the identity just maps to x. And the commutativity of this says that, sorry, keep switching out to m. The commutativity of this is that e acts as a unit on the left, right? There's also sort of a right unit law, where this function is x maps to xe. This is multiplication, and this is the identity. So they're the two unit laws, and then we have this associativity law, which says that if we take three things that we want to compose, we've defined composition in terms of a binary way. So I'm going to run with it. Sorry. So we're reducing this down. We've got three things, and we want to produce sort of one thing, right? So this is x, y, z. This can map to x times y, z. And that maps to x times y times z. Or we do it the other way, right? This maps to x, y times z. And then that maps to the other parenthesization of these three things. And this commutativity of this square says that these two things are equal. So it's just another expression of the associative law in a sort of pictorial way. OK, so that's a monoid. A monad is a lot like this, but we sort of lift it up one level to a functor type level. So let me say, a monad, it's going to have three parts. I'm going to call it t, mu, and eta. And this is a functor. So we pick a category C, and we have a functor t from C to C. right? An endofunctor. So just like for algebras, we talked a lot about, for initial algebras and so on, we talked a lot about endofunctors. A monad is a functor, but we give ourselves some extra structure. We have a natural transformation. So one thing you can do with an endofunctor is you can apply it to itself. You can compose it to itself because it outputs a C, and sort of you get C's. You can put that as the input to itself. So we have this functor t squared, or t then t, right? We also just have t, and they're both functors between the same thing. And we talked about natural transformations as this way of relating functors. This was sort of Bartosz last Friday. So we want a natural transformation mu that sort of takes two applications of t and returns one application. And that's very much what's going on here, right? Second, we want another natural transformation, but this time between two different functors, right? Well, the first functor is again t. No, the first functor is the identity functor on C, right? Given a category C, we can talk about the identity functor on it. We also have the functor t, and we can talk about a natural transformation from the identity to t. And then it obeys some laws, right? So instead of writing, instead of writing just this sort of more complicated diagram, I'm going to just focus on calling the natural transformation like that and sort of ignore the fact that the functors from C to C, right? So this is we have a functor, natural transformation mu from t squared to t. And so we can play the same game where we can draw these squares. Let's call this t of eta, and this one mu. So mu goes from t squared to t. Eta goes from sort of the identity on C to t. If we apply t to eta, which you can do, then we get a map from t to t squared. And so we have a unit law that looks like that. But really, it's the same thing as that's going on with a monoid, just sort of lifted to this more abstract setting. I don't expect you to really interpret this diagram right now, but just appreciate that this is sort of, again, sort of taking this general structure that we use to talk about composition and sort of lifting it to a new setting. So there's a unit law, there's the other unit law, and I'm just going to quickly write down some things here. I, again, don't expect you to completely interpret the syntax if you're not familiar with it. And then there's an associative law. So again, it's sort of a way of going between, there are two ways of going between three applications of t and one application. And so these ways are mu, just going from 2 to 1. And then we can sort of do this thing called t mu, or this thing called mu sub t. We'll get to that in an example in just a second. In fact, I think that's all I wanted to say on that, so we'll get to it right now. Okay. So this definition is really quite abstract. And that's powerful because monads come in all shapes and sizes with all sorts of different intuitions. And it's sort of a flexible, powerful concept because of its generality. But because of that, it's sort of hard to see exactly what that thing is saying. Do you have a question, Alex?
Formal sense in which a monad is a lifted monoid?
Yes, there's a very formal sense. Monad is a monoid an internal monoid in the category of endofunctors for some category. That sort of statement can actually be interpreted, but it's a bit beyond what we're trying to do at the moment because we need to talk about symmetric monoidal categories and things like that. Actually, just monoidal categories, I think. Anyway, in any case, it's beyond the scope of this present discussion. So this is probably part 3. Examples. Right, so there's some sort of data structure there and some laws that we should think about that data structure obeying, but what actually looks like that. So one example is called the maybe monad. We use this to sort of capture notions of sort of non-terminating or partial composition, partial function.
Just to clarify, that mu sub t, should that be mu t?
Mu t, I really do mean mu sub t, and we'll see why in this particular example in just a second, but good question. I apologize for using syntax before I've really defined it.
We're going to talk about what mu sub t means.
Yes, we are. Yeah, I think it's more helpful just to see it in an example, and then we can sort of back out a formal definition of what's going on. So here's a monad. It's called maybe, and I'm just going to define the maybe monad on set. So it's a functor from set to set. What does a monad do? Well, firstly, we need to, maybe is the name, is this t thing, right? So maybe I'll write that down, t. What that has to be is a functor. So this is c. It has to take a set and return a set, and it's going to just kind of throw an extra point into our set t. So here's a one-element set. We take our set x, and we just add that point in. Right? What does it do on functions? It does the thing that the Haskell compiler will derive if you sort of define this type constructor, which just takes the coproduct with some nil, some unit type. And that's, well, let me. So it just kind of, the function, if we feed it an x, then it returns f of x. And if we feed it the unique element here, it just returns the unique element over here. So I call this function f plus 1 in this sort of category-theoretic setting. It's also, we introduced the notion of bimap for, like, introduced that sort of product should be a bifunctor. And coproduct is the same. And so you might write this in code as bimap f and then identity on 1. I saw a question. Is that still around? No. OK. So that's the functor part of the maybe monad. But this data structure requires two more things, right? It requires a multiplication and a unit, similar to like the definition of a monoid. So what do these look like? Let me just remind you, I guess, also what a natural transformation is by example. So what is a natural transformation from t times t to t, or maybe to maybe? It means that for every sort of set x, we have a function from maybe, so called mu x, from maybe of x to maybe of x. Right? And so this is x plus 1, and this is x plus 1. So the natural transformation wants me to specify a function of this type for every x. Right? How do we do that? Well, there's to specify it without reference to x, because it's meant to be specified in a natural or uniform way for every x, we can really only sort of do the identity on x and then map these 2 points to this unique point here, because this is the only point we have sort of available for us to grab. So I'm going to write that identity on x plus identity on 1 sort of co-paired, you might say, with the identity on 1. If you were writing this in sort of the Haskell, this is going to be bimap identity on x, and then either identity on 1, identity on 1. Right. Apologies that the lines are running into each other a bit. And this is a natural transformation. You can sort of quasi-observe that as Haskell would by just saying, you know, this was given in a uniform formula. But you can also check that by sort of saying if you have an f from x to y, then there's a square that you can write down, and that square commutes. Second, we have this natural transformation called the unit, or called eta, and this is a map from x to maybe of x. which we remember is just x plus 1. And so there's also a natural way to do this, which in fact we've already seen, right? It's called something like in to the first factor if you're doing in a more category-theoretic style, or the way we defined it in code was by titling that function left, to say we map this into the left factor. OK, so that's the data of a monad, right? We have a t, we have a mu, and we have an eta. And now we need to sort of think about what these laws say for the monad. And so what they say is I'll write them across here. So we can talk so we can check these. These are equivalences of commutative diagrams of natural transformations, right? But instead of sort of using this sort of packed up notation, we can just, a natural transformation is a bunch of functions or a bunch of morphisms for every object, right? So we can sort of unpack and evaluate this by sort of on each object, by just picking an object and plugging it in and make sure it works for every single thing we could plug in. So that square, or that triangle there, turns into the statement that for all, in this case, sets x, we want, and I'm just going to plug in sort of maybe already, we want this square from x plus 1 to x plus 1 plus 1 to x plus 1, and then the identity function there to commute. And what are these functions? Well, there are in fact sort of two different things expressed by the difference between t of eta and eta sub t, right? So the first thing, t of eta is this function that just is called left. And so if we do apply t to left, what left is doing is it sort of is a map from this x to this x plus 1. And we apply t to that, so we just kind of wrap that in there. So it's going left on this factor, and it's the identity on this other factor. So this function is just including this x to this x and this 1 over here to that one. And the sort of commutative diagram says that we sort of multiply, so we combine these two ones to that one, and that is the identity. So what I want to emphasize is that what's going on is this goes to this, and this goes to this, and then going down here is just exactly this thing going there and this thing going there. So that's the one unit law. The other unit law, so what is t of eta? Eta sub t. What I mean by that is eta evaluated at t of x, right? So this is t of eta at x, and this is eta evaluated at t of x, because we can evaluate eta at every object. So there's an object tx, which is x plus 1, and we can evaluate that. And so what is this doing? Eta tx. So here t eta x, map this thing to this thing and this thing here. Eta sub t of x is just the left for this thing. So it's going to map this whole thing to this whole thing, right? And then the commutative square of the unit law just says that as we go down here, what is this thing doing? Well, it commutes. It sort of this, well, eta sub tx, then multiplying this multiplication of mu sub x just gives the identity. OK. The associative law says what happens if we add 3 points to x and then try and reduce it down to 1 point. Right? We can, and so we've got these sort of two different ways to do so. And what are these ways? Well, so here again, what is t of mu and what is mu sub t? Let's see. So mu is taking sort of x plus 1 and mapping that to this x plus 1. So it's sort of going this thing to this thing. And when we apply t of it, we just sort of tack the 1 on, right? So this is t of mu sub at x. And so what this is saying is we combine these two 1s to this one first. and then sort of combine these two ones down, right? What is mu sub t of x? Well, t of x is x plus 1. So what it's saying is we sort of had this thing, and then we added the 2 points. And then we sort of collapse these 2 points. Mu is collapsing those 2 outer points down to that one. And we're treating this x plus 1, this sort of tx, as atomic, right? So if we collect them and then collapse them. So that's what the 2 different functions are. And you can kind of, I mean, in the end, you're just taking these 3 extra points and saying, well, just make them all the same. And both sort of ways of doing that pairwise commute. So maybe is a monad. So that's a first example of a monad. Let me give you 2 more partial examples and then let you discuss exactly why these are examples. So a lovely monad. I mean, one example is going to be the string example. But before I get there, another lovely monad, intimately tied with the notion of monoids themselves, but in sort of a complicated way, which we might see a little bit of, is the list monad. So list monad. So here we have this. I'm just going to define a list monad on set. In fact, all my examples will be examples on set for this class. And what it does is it maps some set x to lists in that set, right? So it means that, it maps a set to the set of lists of that thing. So what are the elements of this set? Well, we just pick sort of elements of some finite list of elements of x. And they form an element of list x, right? How is this a functor? We've seen this functor before, but to remind you, we can sort of define given an f from x to y, we can define a map I'm going to call list f from list x to list y by, if we have one of these elements, we can apply it pointwise, right? So this maps to f of x1 to f of xk, right? And that, so this is now taking sort of construction from this sort of initial algebra section. So you do this sort of recursive, well, yeah. I won't make that precise, but this is sort of a more recursive world than this one over here. Anyway, okay, so we have a functor. We need to define the sort of multiplication and the unit, right? So here, what is the multiplication? The multiplication says that for all x, we have a function from lists of x, monad applied twice, just to list of x. And what's this function? Well, if we have some lists of lists, so this is sort of x1 to xk, but we have this sort of k1 first list, and then we have a list of these lists with sort of n elements, I guess. So this superscript n is not like a power, it's just, it's just sort of an indexing device. We have a list of lists. We can just flatten this list out. So this function might be called flatten. And this maps to sort of x11 to xk11, and then all the other lists, and then xn1 to xn sub n. It's just list flattening, right? And then I'm also claiming to make this into a monad, we need for every set x a function from the identity applied to x, which is just x, to list applied to x, that's list x. And what does that do? Well, it takes an element of x and builds the singleton list containing just that element x. Right. So that, I claim, is a monad. You have to check the laws, which I'll give you a second to do in a moment. The other thing, another functor I just want to talk about, since we talked about it sort of in the introduction, is just this functor s from set to set, which takes a set and sort of times it with a string. But actually, I'm going to sort of generalize this slightly. I'm going to say, we'll pick a monoid m star unit, I guess. And then I'm going to define a functor times m, which sends x to x times m. OK, so now just to give you a moment to digest, I have two questions for you. One is sort of why does list with these natural transformations, mu and eta, obey the laws, to obey the monad laws, to be more precise? And then two, so I've given you a functor, an endofunctor, but for this to be a monad, it should have some multiplication and some unit that obeys these laws. So what do you think are the sort of multiplication and unit for this functor times m? OK, so why don't we sort of take a break? People can talk to each other for the next 3 minutes and just try and hash out any questions and answers to these two questions. So let's just answer this question first. So why should this list monad idea behave the monad laws? Does anyone want to say, for example, we will just go in order. What does this law say? So what is then T eta?
I think for each element of the list.
Right. So let's double check that. So what is so eta x? Oh, is just written down here. It says it takes an element and makes a singleton list out of it. Right. So T eta is going to sort of map list over that. So it's going to be applying that eta to each element. So it's going to, you're right, it's going to, this T eta thing, which is a map from, so T eta at x, which is a map from list of x to list of x, it's going to take a list, sorry, list of x. Thanks. And it's going to take a list, sort of x1, sorry. Should have left myself a bit more space. I'm going to write it up here. So this map T eta x from list of x to list of x takes this list x1 to xk and wraps each individual element in a singleton list. And then you might be able to see that when you flatten that out, you remove these inner parentheses or inner brackets, and so it just goes back to how it started, right? And then, so what is eta sub t of x? Right, so eta sub t of x, so eta sub t of x takes, it does this on, well, it just takes a list and turns it into a singleton list of that list. Right, which is also a list of lists. And then you might be able to see that if you flatten that out, then you get back your original list. So then it obeys the two unit laws. And what does the associative law say?
Basically, all that's happening is we're rebracketing.
Right. And it's just this rebracketing procedure. So it says that if we start with a list of lists, we've got tons of brackets everywhere, and all it's going to do is just take out all the intermediate brackets in various ways. There are sort of two different ways, but you just end up with a single list without that mess of brackets. OK, so that's that question. What are the multiplication in the unit for this monad? So what are the types? We have mu x, and it's going to map. So we take x, and then we apply the monad twice. And then we return to applying the monad once. So if I have a thing, sort of element of x, and then m1, m2, and I need an element of x times m, what do we do? Right. Well, we apply the monoid multiplication. So we started with a monoid, and we can't do anything with x. We don't know anything about that. But we do know that monoid elements multiply. So we can multiply m1 and m2, and now we have an element there. And similarly, for the unit, we want to map from x to x times m. So given an x, we need to produce an element of x times m. How do we do that? Right. The only way we can sort of produce an element of m out of nothing is to use the identity element. So it maps x to x, comma e. And in fact, you can check that this obeys the monad laws. And how you check that is basically just the fact that monoids are associative and unital. And that kind of collapses down. Yep, question?
You can also compose the two monoid elements in the other direction, like solve them and then like multiply.
The comment was you can compose the monoid elements in the other direction.
Multiply them, like first swap them and then multiply in the other order.
That sounds like to me like you're talking about a commutative monoid, and which doesn't hold in general. But we can talk about that afterwards. Oh, sorry. There is another. You're saying that there is another monoid multiplication that is going to work out. Yes, there is. It's isomorphic, and I wouldn't do it that way unless you want your notation to be really confusing. Oh, okay. Yeah. I see your point. I see your point. You can define like a reverse monoid.
Haskell is actually a reverse monoid.
Okay. Cool. Great. Now, what did I want to talk about? In the last few minutes, let's try and get to hint at where the next couple lectures are going. And just like for endofunctors, where we talked about algebras for an arbitrary functor, we can also talk about algebras from monad. And these are, unfortunately, a special case of algebras for an endofunctor. So that when you say, you might want to be tempted to say, I have a monad M, and you have an M algebra, and if you mean just the underlying functor of the monad, it's a different concept slightly. Let me be more precise about that in just a second. But the basic idea is that these sort of monads are going to allow us a way of accessing basically other categories from the category of, in this case, sets. We have this base category, sets here. When we're thinking about computation, it's sort of more this category of types and functions in Haskell. And we're going to see that over the next few days, or over the next week, that taking, for example, where did my pointed set monad go? Taking this allows us to access this category of partial functions. Taking the list monad allows us to access the category of monoids from that point of view, and so on. We'll see that we can sort of access notions of like non-deterministic computation or probabilistic computation or input-output by using the appropriate monad. So, but back to a definition of algebras. So an algebra for a monad, let's just call it T mu eta again, is an object C in, so T is a functor from C to C. So we take an object C and C, and this is called the carrier. And we have a morphism I'm going to call A from TC to C. And this is called the structure map. So far, it looks like a monad for a functor. Sorry, an algebra for a functor.
Is that squiggle in front of the C there a T?
Squiggle in front of the C.
C is an element of squiggle.
Oh, object. This says objects. Okay. OBJ.
Thank you.
Great. Thanks for clarifying. OK, so we have this data. But now for an algebra for a monad, we're going to subject it to some laws. So it's not going to be all of these things like it would be if we were talking about an algebra for an endofunctor. So they obey two laws. Yes, two laws. So one law, oh, sorry, that's wrong, says, so we're going to start with T of C, and we're going to try and get down to C. So what can we do? Well, we have a map from T of C to C, and we can apply the functor T to it. So that's T of A. and then we get to a T of C, and then we can apply A again. So basically just apply A twice, and we get down to C. But the other thing we have is a monad. We have this multiplication. So there's automatically a way to get from T of C to just T of C, and that's called multiplication at C. And then to get down to C, we can apply A. And so we want this to commute. And the second thing we want is we can go from T of C. It's a unit law. So this is sort of like an associative law. From C. We can go from C to T of C using the unit at C. Thanks. And then we can go back down to C using the algebra map A. But we can also just have done nothing at C.
Can you write your left-hand C?
Left?
Just rewrite it.
Oh, sorry. C. I'm going to rewrite this one too. OK. So we want these two things to commute. And they are the laws for an algebra. So let's, for example, talk about list algebras for the list monad. So what this is saying is that I need a map from, let's call the carrier M, and then the structure map, I don't know, F. Sorry. Let's just call it A. So a list algebra is a map from list M to M.
Is M a set?
M is a set, because list is a endofunctoron set, and M is an object of the category set. OK. So what this does is it takes a list of things, x1 to xk, and then combines them down to produce this single thing, right, which is just A of that list. So what are examples of ways to take a list and produce a single element? Right. The folds over some list. In particular, one way to get a structure like this is to use a monoid multiplication. So I can map this to sort of just multiplying out the list. I can fold the monoid multiplication over the list. And I get a function like this. And so what do these sort of laws say? They say that if, in this case, if I pick a monoid, say the natural numbers, what it's saying is that if I have a list of lists, I can sort of multiply the elements of the internal lists and get a list of elements, and then multiply those elements. That's this way. Or I can just get rid of the bracketing and multiply everything at once, and that's this way. And it says that those two things are equal. And so it turns out that that forces this thing, in fact, to be an associative operation. And with this law, it's going to say if we produce a singleton list and then evaluate, it's the identity. So if we sort of take the singleton list and remove the brackets. And where does it send where does the algebra map have to send the singleton list? It has to send it to the thing we started with. So those two things, in fact, imply that list algebras are monoids. And so just to wrap up, somehow this notion of the functor list, which you might have remembered we constructed recursively using this sort of nil-cons type constructor for lists. These things return sort of the essence of the notion of a monoid, and so you can recover what's known as the category of monoids from sort of this category of algebras for this monad. And so we'll see how that basically this is a framework for allowing us to talk about monoids from the point of view of the category of sets. And so even if we're restricted to living in this category Haskell, we can start to access these other algebraic structures through this notion of a monad. But I'll wrap up now and leave the rest of that story to next week with David and Bartosz.